Good afternoon. I am Ed Sperling. I am the editor-in-chief of Semiconductor Engineering. And we are here with a truly stellar cast today for scaling 3D IC technologies from niche to mainstream. All the way down at the end, Jeff Kane, Vice President of Engineering at Chiplets. Next to him, Letizia Giuliano, VP of Product Marketing and Management at AlphaWave Semi. Dark jacket, right next to her, fumbling with her microphone, Lalitha Eminemi, the Vice President of Architecture, Design and Technology Solutions at Intel. Subi Kangari, Vice President of Systems to Materials at Applied Materials. Deepak Kulkarni, Senior Fellow at AMD. And Tony Mastriani, Senior Director of 3D IC Solutions at Siemens. So, first question for you. Which industry sectors, AI accelerators, network infrastructure, mobile, automotive, currently will see significant benefits from 2.5D and 3D? And why don't we start there? Jeff.
Well, I would argue AI wouldn't be where it is today without some type of 3D integration and 2.5D integration. It's really led the way. Will the rest follow? Probably at some point, yes. But typically, automotive has a pretty slow cycle, lots of qualification work. But I would argue AI has been driving this whole thing, basically. It's really been the catalyst for pretty much all of this.
Letizia.
So testing, yeah, so I definitely agree with that. I would like to say that maybe 99% of all the ISoC we're building today are chiplet based. So 2.5D, definitely with the interposer type of design, and we have many ecosystem around interposer design coming from different foundries. And we don't fit in a reticle size, so we need to disaggregate. We need to disaggregate through the 2.5D. Also, we need to go start looking at stacking devices. And the good news is not just company like Intel or AMD doing it. There is also others that are now enabled to build 2.5D design and 3D design. So the ecosystem is expanding. And at AlphaWave, we are enabling it through our chiplet-based architectures that can be in form of IP subsystem, but can also be in a form of chiplet already made that people can integrate. And also in collaboration with Siemens, we are enabling not only IP and subsystem, but also how you verify this subsystem, how you put these things together. So it's very nice to see now, again, people that can unleash all these tools to build disaggregated system, and it's been interesting.
Lalitha, where do you see Intel?
This is why I was feeling with it. Okay.
Yes.
So anything with AI, large language models, anything to do with HPC, server scale segment, I think will benefit the most from disaggregated technologies and then hence 3D IC. I also don't think monolithic packaging will go away, right? Any segments that are maybe a little bit more cost sensitive, maybe IoT, those kind of areas where you're really looking for a very quick, fast time to market. I don't worry so much about the performance or the cost. I think they will stay back in monolithic. I think there is a space for both based on the segments that you're trying to address as a company.
And Subi, coming from the material side, where do you see it happening?
Yeah, so your question was where is 3D IC actually, which segments, right? I mean, if you really look at it, mobile has been using it for a while, but for a different reason, right? That is more of the form factor driven primarily. But now with the AI and HPC, it's more for performance. What are the other ways that you can get your performance? So there's a different reason why it's getting in there. Of course, there are quite a few challenges with that, which I think we're all going to talk about later on. But started with mobile, and now AI HPC is driving the 3D IC.
And Deepak, obviously AMD has been working with chiplets since about 2007, right?
Yeah, thanks for inviting me to this panel. And I was about to start by saying we've been on a journey for almost 10 plus years now on chiplet technology. And so I myself have been on panels like this for the last 4 years saying chiplets are the future. So maybe the next time I'm here, I would like to hear the question turned into, are monolithic SoCs still viable? And what areas or segments would we continue to utilize them? I think Lalita brought up a good point in terms of cost sensitivity, and looking at monolithic devices for some of those applications. But I think if you look at AMD as a company with a vast portfolio of IP, one of the challenges that we see is if we need to customize any individual product segment to run as a monolithic SoC, I'm having to build customized IP now just for that purpose. So if the bulk of my costs are design, tape out, validation, then I would much rather continue to utilize chiplets than create a separate work stream to justify a monolithic product.
And Tony, you have sort of an overview of the whole industry at this point from your vantage point in EDA. Where are you seeing it actually taking off?
Yeah. Actually, everyone talked about the hyperscalers have been doing this for some time, and they've been bleeding edge. Automotive is starting to adopt it. Some of the traditional automotives are a little bit behind, but they realize they need to keep up with some of the more advanced. We're seeing right now through the CHIPS Act, the Mil-Aero and defense industries are really, they need this technology. They can't afford to put large teams and custom designs, so they're quickly trying to get up to speed to adopt these technologies. So we're very active in some of those programs there.
So most of the chips that have been developed on 3D-IC type of processes are still in development right now. They've been targeted toward a lot of the AI data centers. That's pretty much where the money is at this point. And a lot of these will never be sold commercially. I'm curious, do you see these as a real market, or is this just going to be a few customers that are going to drive massive demands? Deepak, why don't we start with you, and I want to go to Lalitha next.
Yeah, so sure. I think the AI accelerator and the networking segments definitely leverage chiplet architecture because of the need for bringing in high bandwidth memory on package, as well as the fact that we are hitting reticle limits and need to build larger chips. But I would give 3D V-Cache as an example of a commercial solution that's been around for both mobile laptops and desktops for the past 3+ years. And it's been very successful as a commercial solution. So I think if the performance that 3D-IC provides is there, you will see adoption across multiple different product segments.
So within a company, I think as Deepak suggested, reusing an SoC, absolutely. I think that is one point where you can make that particular die reusable across various segments, like how they do it, right? But if you are looking at, and probably that's true of Intel too, but if you look at, can we make these chiplets commercially viable? So that utopian concept of having a chiplet marketplace where I do have this perfect chiplet, I just take it and then I stitch it up with several other chiplets and packaging and build an architecture, right? For that kind of a commercial viability of an SoC, I think you do need a little bit more work in the ecosystem. You need to have standards, you need to have very clearly defined performance specs, right? All the technology targets, all the product targets need to be there along with it. Within a company, I think it's okay to do. But if you're looking at these chiplets that are viable to be used across the industries, then I think that's a different ballpark.
And Letizia, when you think about 3D-ICs, it's been said that by a number of people that it's all about the interconnects. Mm-hmm. It's all about moving the data from one area to another within these multi-die systems. Where do you see this? What sort of problems are you starting to see with that, if any? And do you see an uptake in terms of this is actually a growing type of market, or is it still sort of narrow and everybody's experimenting?
So when we build system in package, we are solving a problem how we disaggregate this system, right? We used to have everything monolithic, everything was going within the die. So now we need to divide the die and try to figure out how to do that. So actually there is a lot that goes into planning this, and defining a die-to-die interface is very optimal for each type of disaggregated system. So what I see is that each bandwidth requirement, each package technology does require a dedicated, I wouldn't say the word custom, but I would say the word dedicated solution for die-to-die. Because there is no one configuration that fits at all. So if you have a standard package, or you have a 2.5D embedded bridge, or you have a different type of interposer, there are different ways of addressing the type of channeling interconnect. So what do we see is having a flexible type of interconnect solution can address this thing, but needs to be very dedicated and configurable for the type of interconnect. And it's very key to do it right, because you can mess it up in sense of power, area, and latency if you don't build that piece of interconnect optimal. Because it's very easy to over-design, it's easy to break up your power budget, your latency budget, if you don't target correctly. And everything starts early on from the package design, which type of package we use and which type of bandwidth density we want. So it's a lot that goes into now architecting these things from the beginning. Yeah.
Subi, a lot of these devices are now looking at completely new materials. We have structural issues, we have thermal issues, we have all sorts of potential blockages and things that can go wrong because of materials. What are you hearing from your customers?
Yeah, so actually, I want to take a step back first and make sure that we're all aligned on how the chiplets really evolved. Just 1 minute, right? There are three reasons, basically, right? I think just so that we set the stage. Deepak, I mean, you guys really drove one of them. On the leading edge, the leading adapters of the technology, and when they saw the defect densities, it's always going to be a big challenge as you go advance the technology node. So they wanted to break it down to smaller chips. That's one of the reasons why the chiplets came into existence. The second one was, I think she touched upon it, the reusability of the design from the previous generations. The analog and the memory doesn't necessarily scale at the same level as logic, and sometimes that is in the critical path for design, so you try to reuse it. So that's another reason why the chiplets came in. The third one was something that always was there, we had not really seen it as chiplets, which is the heterogeneous integration of functions, right? At the end of the day, every function, RF, high voltage or power management or memory, whatever you want to think about, have their own respective optimal technology, and you got to go process those. You bring them together. That's a heterogeneous integration. Those were the real reasons that chiplets really came into existence. And now, with all the advancement that we're talking about, we're trying to put that on very advanced packaging, because you want to have the same level of what you just said, signal integrity, the power integrity, and the thermals that you want to solve, is the new set of challenges that's all coming together. And what we see, I don't know if you all know, we spend about $3.5 billion in R&D every year as Applied Materials equipment provider. We have to stay ahead of the semiconductor industry, and we're always looking at what the challenges are, what the inflections are, and we have to be prepared. So going back to your original question, some of the things that are coming together is when you look at 3D-IC, I always see 3D-IC, because when you ask the original question, there are two parts to it. One is people synonymously use it as chiplets when you say 3D-IC, but some people see it as packaging because, in fact, they have to come together. So in terms of the materials, I mean, there's a lot to talk, but in summary, the challenges are, for example, in the 3D-IC, HBM is one of the first ones that is using or pushing the technology limits of the stacking and the 3D. The microbumps, scaling the pitches there, the EMI, the thermal reliability challenges, those are all the issues that we're really seeing, and we are always constantly looking at new materials and new ways of trying to improve that, and that in itself is a big story. But remember that bringing in a new material from a discovery to bringing it into a real product is about 15 years. It's not easy, but we're trying to speed it up. We're trying to do AI, use AI and all of that. But the biggest focus has been on solving some of the thermal coupling and thermal challenges besides the reliability for fine pitch. those are the real focus areas.
May I add a little bit of a piece? I think I do worry about when you say putting chiplets together is just not an architecture exploration or a design challenge or an EDA challenge. It's a technology challenge, right? It's materials. You got to come up with low loss materials, whether it's for thermals or high speed IOs. I mean, there is a lot that needs to go on technology. For instance, if I offer Intel packaging on an external vendor process, right? Not Intel process, which is what we typically do now with all our customers. I need to certify something like a bridge with every variation of memory, HBM, HBM3E, HBM3, HBM4. I need to validate it against the N2s and N3s. I also need to certify it against the die-to-die protocols like UCIe, you name it, bunch of wires, Alien. The technology readiness of enabling with this 3D IC when you are mixing and matching various foundry processes, packaging, die-to-die interconnects, I think is a way bigger problem than having systems, lightweight systems that actually let us do the architecture. I think the technology portion, I think, still needs a lot more work.
Let's get a couple more commentary, and then let's dig into this. Jeff, where do you see it actually starting to roll out, if anywhere, at this point?
So Chiplets is actually working on next generation 2.5D substrate technology. That's what we're doing, right? We want to eliminate reticle limits. We want to eliminate, we want to go back to the OSAT model. You get your die from wherever you want, put them together, put them on the package, off you go, right? So, in our mind, this technology is brand new. It's really, really quite new, but we think it'll be ready sometime Q2, maybe Q3 of next year. And so we think that's when it's all going to start. So to get rid of all those limitations, to, not be die dependent on one supplier, that's our vision.
Tony, where do you see this starting to roll out here, and how real is it?
Yeah, well, there is quite a bit of development that's going on right now in larger substrates. Jeff mentioned it, reticle size, but we're talking like, half panel size type. So it's a few years out, but that is going to enable, massively large systems. So we need to start thinking about how we're going to design those. We're going to need AI to drive that. The complexity of these systems is really going to be daunting. So we need to get the tools to work together, the technology challenges. It's not just the packaging problem. It's a system problem. It's packaging. It's physical design. It's chip design, thermal. It's everything. And these tools need to work together, and they really weren't designed to work together. So that's what we're focusing on is to put together cohesive workflows with each of these tools. The other important thing we need to do is manage the data. You have a lot of data from different management, so we're building that into the workflows. That's an important concept. And actually developing that as metadata, and that will lend itself to AI-driven approaches. And the last thing is the ecosystem. So there's been quite a bit of effort, 3D blocks from TSMC. They're driving that as an IEEE standard. And then we're also very actively involved in the OCP, the 3DKs, where we're trying to get standardized machine-readable models that are adopted by and EDA neutral. So at least we have a little bit more interoperability. So things like material design properties, we'll put that in a machine-readable format. So this can be used by your scripts and your tools, as well as be a little more AI-friendly. Chiplet design kits, standardizing on what models get delivered with the chiplet. If we are going to have an open marketplace, you need to have a clear definition of what models get delivered with that chiplet.
So one of the reasons behind 3D ICs is that we basically run out of room to put it onto a single die. There's only so much you can fit into the sides of a reticle, and stitching them together is rather messy. So the problem that you run into here is that you've now dealing with heat that gets trapped inside these designs. The question is, how do you get it out? And this has been slowing things down. I think I talked to Intel going back around 2016, and they were still lamenting the fact that they couldn't solve this problem back then. Here we are 9 years later, and it is still a major problem. We are building in redundancy because these circuits are aging faster under high thermal loads. There's much more density that is required in terms of the transistors. You've got active cooling, which is going to be required. So how much does that eat into the performance and savings? This was billed as the next generation SoC. We're shortening the distances. We're adding very fast interconnects to go through it. How much can we get out of this? Deepak.
Yeah, I think it is definitely a challenge as you put together 3D stacked die, because in essence you are maintaining a similar footprint to your monolithic SoC, but in some cases have doubled or tripled the power density within that footprint, right? But I think the best solution to this has been looking at this more holistically and saying it's not a thermal problem, it's not a power delivery problem, it's a system optimization problem. Right? If you stack your highest power device at the bottom of a stack, you're going to have a thermal challenge. If you put your highest power device at the top, you have a power delivery challenge to the rest of the stack. But if we truly get into a stage of saying, I'm not designing monolithic two-dimensional SoCs and then leaving it to the packaging folks to figure out the thermals, but start with a system level view of things, I think there are optimization points. It's not a free lunch, but there are optimization points where you can balance the power delivery, the thermals, as well as the performance. And keep in mind that there is a very heavy penalty from an energy perspective on transferring data between chips, especially in the AI accelerator segment. So if you look at it holistically from a system perspective, you are designing energy efficient solutions that will perform better than many chips talking to each other over a network.
With I know 9 years later, have you solved some of these issues?
No. I think there is Deepak knows. There is liquid cooling. There are a lot of material advantages that are happening. But I think it's a tough problem to solve. And as he said, when you are looking at these power going into like 3 kilowatts to 5 kilowatts, one burden that probably needs to go back a little bit more is on that co-optimization piece, right? Where you are looking holistically as you're coming up with a product specification, where you just don't say, I'm going to throw all the kitchen sink at it and then figure out a TD person on how to remove the heat. Maybe a better way is to look at how you design those chips, how you interface it with the packaging folks. So you are doing trade-offs between the power and thermals. In traditional monolithic, what we used to do is people would finish up the SoC design, they would throw it at us, we would do thermal modeling, and we would tell them, these are the areas of your SoC where there might be some thermal contention. I think that needs to be a norm now when you're coming up with an architecture. So just the same way we do, I think thermal aware designs has to be a norm at this point. When you're going to these large language models, it's only going to get crazy. And you are probably looking at a 3D silicon scaling. And at that point, I think the technology development needs to continue with materials, with smarter ways of removing heat from this complex architectures. At the same time, the way you design, it needs to step away from that monolithic aspect. There has to be a complete paradigm shift.
Subi, to Applied Materials, everything is a material. So how does this get solved?
No, like both of them said clearly, packaging used to be an afterthought, for a long time, right? You design it, throw over the wall, and then go make it, get it packaged. But today, advanced packaging is at the forefront. At the time of the architecture, like Deepak said, it's a system solution, and everything is being looked at with the co-optimization. But having said that, you're still pushing the limits. For example, when you're on a monolithic SoC, your gigahertz signals are running on the silicon short distance, and you're able to manage it. But with the chiplets and the 3D IC that we're talking about, now those signals, very high performance signals, are now running on the substrate to some extent, at least, depending on how you partition it and what you do. And in some cases, it's inevitable. So that is like, a Ferrari running on a country road, right? It's not easy. because you have to get those signal integrity right, and therefore new materials, right? I'm just getting down to that part. So, which is why the industry is looking at different substrates, right? Whether it's glass substrate or something else. That's not the only reason, but that's one of the reasons. You want to get the right form factor, right pitch, right beachfront, and then signal integrity with very fine resolution, which you cannot easily get in an organic substrate. And so those are the kind of new materials that we're looking at it from that angle. From a thermal point of view, there is a lot of research going on in you're trying to use different types of materials for heat elimination. And then on top of all of that, there is also the EMI that you have to worry about. You cannot just ignore that. Then there is the power delivery that they all touched upon. There are different ways of doing it. That's not all materials, but to some extent it's design, some extent it's technology with the backside power, integrating the voltage regulators much closer, different types of capacitors, decaps and inductors. There is some material innovation that's happening. In fact, we have some new forms of inductors and capacitors for very high density and being able to embed it. So material is all over, right? And there's some real fundamental material innovation that is also happening. But like I said, material innovation getting into product is a long, long cycle.
Well, Tizzy, when you're designing chiplets, what do you have to think about here when you get into 3D that you didn't have to think about before?
We heard that we start involving the package start early on. So no, it's not anymore an afterthought. So my best friends are the packaging team. So how we take benefit of the package technology in a way that allow us to disaggregate correctly. And the other things that probably we didn't mention earlier, we talk about is the ADA enablement about designing 3D packaging or 2.5D. So we really involve early on our ADA partners to make sure that we have all in place to design a chiplet. And that comes from pre-silicon validation, so how we validate disaggregated system and two chiplets coming together, how they can talk to each other, but also is signal integrity, power integrity of these in-package routes, and also thermal. And I'd like to say something about thermal. We still have, we've been talking about chiplet now, at least in several forums, how we do it, when we do it, but we have not solved yet from the ADA perspective how we handle and how we simulate for thermal. So that is, I think, what we're gonna talk next year. We want a solution up here, right? How we're gonna, what we're gonna do that. So I think it's more involving all this part, the package, the DDA early on. So our architects are now more involved in all these type of topics that you used to be before. Yeah.
Yeah, I want to pile on this too and give Siemens a little plug here. So obviously the designs we're talking about doing in the substrates are extremely complicated, right? When you have that much RDL and a couple layers, it really gets complicated very fast. And the only tool we've ever done a chiplets design in is XPD. The competitor's tool does not work. Okay, it crashes it. It can't not handle the size of the database. So as somebody relatively new to the packaging business, what's obvious is, especially like layout and SIPI tools, those all grew up out of the boards, right, out of the PCBs. It would have been a lot better for us if it had come from the other direction. So just FYI. And piling on the thermal, I got a good buddy at Arista Networks. Anyway, he worked his way through college as a mechanical engineer. He was a licensed plumber. Well, now at Arista, he's the first guy that gets to go talk to the customer because he gets to teach them how to turn their data center into a giant plumbing factory. So just thought that was interesting.
Tony, a lot of these designs are one-offs. Do the tools that you're developing, do they work across all, regardless of how this is going to be applied?
That's what we're trying to do. We're trying to build general platforms that will address all these problems, and then we'll have, yeah. Yes. So what we're trying to do is have common platforms that will solve all of these problems, and it's going to be incremental, but we don't want to do one-offs here or there. So we do need to fine-tune for the particular technologies, and we'll do that, but we want to build a foundation. Just to continue a little bit about the thermal problem, like we all talked about, you can't wait to the end and hand that off to a mechanical engineer, once the design is done. So you have to start earlier at the architectural level. So what we're trying to do is have predictive analysis. So as you're doing your system level modeling, you can have estimates of your power, and we can actually do thermal analysis and power analysis at that level. And the other thing is, rather than reaching out to that mechanical engineer, we're trying to address the challenge to the persona who's running it. So if it's a chip designer, we have an environment that will enable a chip designer to actually run thermal analysis on a single die or a stacked die. And then we're doing the same thing in the packaging environment. So the package architect can actually run thermal analysis of a complete design with all the things, all the chiplets in there and the substrates very early, and then continue through sign off. And then the last thing, kind of tying in with the previous panel that we did with the software-driven hardware, if you have a complex system with dozens of chiplets in there, what is worst-case power? I mean, if you worst-case it to death, it's not obvious. So by being able to run actual software workloads on those systems, we can actually run, a tremendous amount of simulations on hardware emulators and figure out what those worst case realistic power scenarios are. And then we can simulate those rather than just, margining ourselves to death and assume every chip is going to be running at the same time.
So let me follow up on that. Given the fact that these are exorbitantly expensive chips to develop, some of the 2.5D ones were $100 million. These are going into probably significantly more than that. People want to get their lifetime out of this. They want to get their investment to maximize it. How long are these things going to last? What does silicon life cycle management look like in the era of 3D ICs?
Yeah, well, I think there's going to be a lot of work that needs to be done, to look at that. We don't know, but clearly you're going to have to simulate these things, right? You can't just do a simple reference design and apply that to every design. So you will have to do thermomechanical stress analysis. You have to do thermal analysis. So that's the first step. But we are going to need that reliability data. The other thing we're doing is embedding sensors on the chiplets. You have to do that. You don't have direct access, when you start stacking die. So you're going to have stress sensors, thermal sensors, as well as aging sensors. So that's going to be, absolute requirement. And you'll have to monitor those, throughout, not just when you're testing the part for a manufacturing handoff, but as the part's operational, right? In an automotive, you're going to be running those tests in real time, every time you start up the car. So but again, guys like, Applied Materials and the OSATs, they're going to have to do, and even the AMDs and the Intels of the world, they're going to have to do this reliability testing. And we're going to have to correlate that with the simulations that we're doing.
Okay, Subi, what does reliability look like from a material standpoint?
Yeah. So, but let's take a step back and look at one important thing. The point that you brought up is really important from an economics point of view, right? Of course, the industry is growing. We're going to double from $500 billion to $1 trillion in the next 5 years. Hopefully, all that is correct. So, what took 50 years to get to 500 billion, we're going to get to the next 500 billion in the next 5 years, right? So that means since it's growing, the economics will probably still work out from what we see. The chiplets are going to help it to some extent in terms of the reusability and some of that, at least that's the hope. But no matter what, everything we just talked about, getting it right the first time is super key, is super important, right? We just can't afford to have cycles of learning on that is super expensive. So to that extent, the sophistication of the EDA tools are going to become even more important to make sure that we have everything accurate as closely as we can get, and to be able to emulate all of that up front. And verification is one of the biggest costs, and I know they can vouch for that, in whether it's substrate design or it is SoC design or integrating all of that from a system point of view. So we still need to improve on the EDA tools and get it right for the 3D IC. That is going to be a huge cost saving, obviously, and of course, getting into market is also going to be important. From a material point of view, reliability, any new material the assessment of the performance or the power advantage or of that honestly is very easy. That's not the biggest issue. The real big issue in trying to qualify a new material is all about reliability. And when it's same issue today with the substrate, same glass substrate has been in research for 20 years, right? I mean, 15 years at least. But the issue is how do we make sure it's reliable? So we are doing everything we can. Of course, we do use EDA tools even for that one, besides the actual learning. But EDA tools are getting there from a 3D IC system integration point of view and from reliability point of view, but still there is some scope for improvement there. I would say that openly.
Is it really first time right, or is it lots of little iterations that get you to the final test?
It has to be iterations. I mean, I think one of the things that I would say, and by the way, kudos to all the EDA suppliers. I know this is hosted by Siemens, but in terms of some of the co-design capabilities they have developed, recently we did simulation with an EMIB with TSVs and embedded chip caps, and I didn't think that modeling would work. It worked. So I think for 3D IC, there is lot of innovation, lot of support from the EDA suppliers. So special thanks to Siemens. I think where we need to go is every time I do a different architecture, we don't have the burden. I'm talking as a foundry, right? And I'm not design and technology solutions now, and I'm advanced design and customer enabling. So I meet with customers all the time and I see it. We really cannot do the detailed millions of dollars worth of development and throw resources at it every single time there is a complex architecture. And I think that's one area where EDA can help. And this is where I want to go. I want people to pursue digital twin as a thought, right? If I give you the material characteristics, if I give you the architectures, can you not tell me if there are going to be any undulations, any DLAM concerns that I get into? And then the next part is the thermal mechanical modeling, where if I give enough information, again, this is just a guidance of telling me you are jumping off the cliff, right? We don't want exact answers. I think there is in parallel technology development that happens, but kind of moving from the lightweight, I'm going to let you do co-design, to doing a virtual representation of what the product architecture is. Can we not do, if you give you some target specs, how this would react, right? I think I know digital twin is something that Intel is currently working with NIST. I know there has been some conversations with EDA suppliers, but I think that's one area we want to look at it more as a pathfinding exercise, because that will reduce the time it takes to come up with a decent landing zone.
Deepak.
There's a lot there. So maybe let me piece this together into a few different buckets. First, when we look at it in terms of technology qualification that Lalita talked about, the fact that I could use that chiplet in many different architectures means it could be in a 2.5D setup, it could be in a 3D setup, it could be in a monolithic SoC setup. And so you really need to step back and start asking, what am I defining about this chiplet upfront? Because this chiplet is going to be used in many different ways for many years to come. Because I don't have a restriction anymore that it needs to transition to the next node. As long as that particular IP block can continue to use a legacy node, that chiplet could continue to exist. So there's a portion of this where from a technology development, you really need to think about the various different use conditions for that chiplet and have an enveloping strategy of qualifying it so that you're not iterating through every product implementation. That's definitely an important piece. And when you're going through that qualification, yes, having the ability to do some of this based on simulations will be beneficial. And definitely we will leverage AI-based models, surrogate models, so that we don't have to do a fundamentals-based simulation every time. Although we might still use that for sign-off, at least from a design exploration perspective, you would probably have an AI-based model. But I think there is a portion of this that goes back to what you started the conversation with, Ed, on. If we talk about commercialization of chiplets, what does it really look like? And I seem to keep coming back to What we'll really commercialize is IP blocks. It may not be the chiplet that gets commercialized. We have an ecosystem today for going to an IP vendor and purchasing an IP, and you need a company like AMD that is going to then integrate that into your custom SoC. But would you be able to predict a priori exactly where this chiplet falls in the stack and design it so that everybody could use it? I'm still not there yet. I almost feel like we would default to an IP validation vehicle.
I would like to add something on this. So definitely we do benefit from, the pioneers of chiplet, I always call. So people like AMD, I was in Intel for a long time doing Foveros, another chiplet, and Ponte Vecchio was one of the big examples that we did. So definitely that where we need. But it's not, IP standalone is not just enough. Even the IP itself, even for a monolithic SoC, IP was not, it was a dream of reuse. But still we moved from the IP to the subsystem because it was not even enough to have just a PHY or a controller. We also want a subsystem fully validated because that was also an assurance of something that will work. So I think we need to move the problem now to have reference architecture for people to use because we have to move to chiplet. We cannot live on monolithic anymore. So we need to start moving the ecosystem and having more pioneers that are going to settle and making more that everyone else can use. So we start building more reference design that will start from chiplet architectures, modeling of how we build chiplet together, modeling of the package, digital twins, for other people to do it. So, and I think that in AlphaWave, we start being one of the pioneers of building reference architecture for people to use. We cannot solve all the problems, but in our little things, we definitely solve the problem how to do connectivity chiplet in a way that people can reuse. As an example, we took the connectivity need for an AI accelerator in terms of scale up and scale out, so little Ethernet and PCI Express, how you enable Ethernet PCI Express in a form of chiplet. That was a big problem that we solved so that people can reuse it. I don't pretend to say that is a solution that fits at all, but it's a reference architecture for people to take it and adopt in maybe different type of form factor, different type of power points, or different type of performance points. But we have to do that because we need to move the ecosystem that is going to be AI now, maybe later other type of application in inference or mobile is coming up and automotive is coming up. So we need to help the ecosystem to build a type of reference platform. So I don't like to talk about chiplet marketplace. I think what we need to talk about chiplet ecosystem and reference platform. Yeah.
Somebody's alarm's going off. Must be the heat in this panel. Go ahead.
No, I said if you can get your mic closer.
Go for it.
No, one quick comment is, like, I think where we're heading from what we can see is standard-based IP. Okay, fine. That's one thing. A commodity that is that has to be there for whatever reason is fine. But every company brings value with their core expertise. There is AMD has their own products and there's core IP. Intel has their own. NVIDIA has their own stuff. So that part will never become a commercially viable, available chiplet or IP, whatever. That's going to remain their core business. But in terms of standard-based IOs or IP or whatever core IP, that's okay. That can become, and it'll help the whole industry speed up, because that's really, I don't want to downplay that, but the point here is those are necessary, but that's not really adding the real value to the whole SoC. Those kind of things will continue to be chiplets, and that's where the first commercially available chiplets will come into play.
What tools?
No?
Yeah.
Maybe one question kind of building on this. If we take high bandwidth memory as an example, do you
That's
call
a
it
good
a
one.
chiplet? Do you call it a reference design? Do you call it an IP specification that is then customized by each vendor that builds it?
So HBM is a good example, of course, of this chiplet, and we should acknowledge that HBM came from a standardization effort coming at JEDEC, and there was a lot of push there. But it's also true that the standard HBM is a reference that even AMD or Intel are customizing in a way and bringing it to be something else, right? So let's look at going technical on the bump out and everything, right? So we have bump out from the HBM JEDEC that can be routed on interposer, can be routed also in INMIB. So we have a reference example coming from JEDEC that then can be also customized and dedicated for something else. So that actually HBM is a good example of a workflow that should be pushed out to other markets and other application-specific chiplets.
I'm with Deepak on this. I mean, I think where is the product differentiation if we just take bunch of chiplets that are commercially available and all that as companies we worry about is the die-to-die connections. That's no product differentiation, right? So there is custom. I think that's what I worry about when I hear chiplet marketplace where I go, I pay some money, I get a chiplet, and then I just focus on die-to-die connection. That's no product differentiation, I think. So the IP block aspect is what can be standardized, and that's what can be used.
But that's how the IPs also evolve, right?
Yeah,
So
yeah.
what IP was 10 years back is chiplet today in a way, right? That'll continue the same way.
I'm not going anywhere near the HBM argument. I've gotten in trouble with that before. What do we need in terms of tools that we don't have today? Well, can we test these things? Do we have the capability of really digging in and saying, hey, we know this is operating properly, we don't know? Is it all just internal monitors, or there are actually better ways of dealing with this?
I think most of the tools exist today, but they don't work together. So that's the area we're focusing on. But there is going to be a need for more tools. You know, stress analysis is going to become critical for these, you know, much for the complexity of the designs we're talking about and the feature sizes. So there's going to be advancements in those tools. And again, adapting the persona usage of that. You know, some of the tools that, you know, a package architect will have to use where they're not used to that. So we have to kind of bring it into an environment to make it usable for them. Photonics is an area that's really hot, and we're going to need new tools and workflows for that as well. But that is going to help a lot with the I/O power problem. And RF analysis, you know, when you stack die, you know, there's a lot of development going on in that space. That's going to require new tools. So there's a lot of research going on through government and research organizations, and we're going to have to continue. But this is what's coming down the pipe. And, you know, we're working with them because we can't wait. We have to be working in parallel, trying to keep up. EDA will never catch up to the technology, but, you know, by definition, the technology always leads. But we're trying to close the gap, just like on the material side. We can't afford, you know, 5 years. We need to move quicker than that.
I wouldn't add more tools. I would extend the existing tools
Yeah.
for some of the newer use models.
Absolutely.
Right?
yeah.
Otherwise, integration of these tools becomes a much bigger issue.
Right. And we're dealing with a lot more capacity. So some of the tools are running out of gas. So we have to look at new architectures for the tool. And AI is definitely, it's happening now. It's going to play a bigger role in how these tools work together with agentic AI to, you know, to be able to interface and have these tools talk to each other.
Yeah, it is getting more complex, more variables, multiphysics, you know, so many things that you have to be looking at. And like Deepak said earlier, it's a system level optimization. So the variables are a lot more and the tools are getting more complex. There's no question about that.
Are we going to get to the point where we're going to say, okay, let's at least come up with the 80-20 rule, where 80% of this works, we know we can prove it. 20% is the add-on, where you say this is your capability for what you can change. I've been hearing that from some of the leading foundries. I won't say names here, but that's one of the things that's on their agenda that says, hey, here's the platform, here's your choices, this is what you get, and we'll get it out the door faster.
Yeah, I think that makes sense, right? So maybe that goes to what we were talking about earlier in terms of a reference design. That we can basically say, I can't validate every possible scenario that you'll use this, but I have validated one. And by the way, I provide you with a simulation environment where you can evaluate other options and see if they still fall within the same bounding box. And so, in that sense, having this true vendor agnostic platform where people can bring in different design environments as well as analysis environments, but also bring in their own historical data of validated chiplets, because that's one of the key technologies or IPs that each company now owns. It's here's all the validated versions that work. And so that can be part of what you use to quickly validate a new instantiation of it, because you're using AI to be able to infer what that new instantiation looks like.
Jeff, you're working in a world where you probably have that capability to be able to add in almost whatever you need, right?
I don't know about everything we need, but we've come a long way. Like I said, a lot of help from Siemens. Like, give you an example, right? We were struggling. Our DC power delivery is very unique, and we were struggling with it. Well, they actually wrote a script for us that tied Hyperlink's DC to XPD, so our layout engineers could actually look at hotspots in the design as they're drawing it. Right? It's little things like that that help create a better product at the end of the day. We had a lot of work to do with Siemens. We were embedding a lot of components in our substrate, and we had a lot of work to do there too. And so there's lots of unique challenges. But like Tony said, the technology should stay ahead of the tool, right? That's kind of important, actually. So I think from that standpoint, we're pushing along pretty good here. We're getting some really good results, and looking forward to getting this thing out the door.
I think EDA tool development, I think it should go more ahead as the technology is getting developed. I think there needs to be a gap analysis rather than telling them how complex it is, which I learned, by the way. So as we are deploying the package assembly design kit, you're figuring out just saying that I'm good at technology doesn't help. How do you let the customers do design enablement with some ease of use gets much more critical. So a couple of the things that we have been doing is, as we are, and that's how we work with Siemens too, is as we are doing the technology development, as we do the test chips and the test vehicles, we are basically saying, hey, I'm adding 60 bridges in this. I'm using your tool because I still need to validate. If the test chip doesn't work, then technology development takes seat quarters back. And I think that's where the conversations should start, where I think the EDA development should go along with the technology development. So, there is a design enablement piece that becomes much more critical for foundries.
I will take that even one level before that. We should engage at the material discovery level.
It's all of the above. We have to
That's
work
how we
with the
address your
foundries,
thermals.
We have to work with the OSATs, the material vendors, also the designers. We have to work with the people who are developing these advanced designs, right? So we need real test cases. So we are proactively, trying to reach out and, to build prototype flows with the designers and solve them problems, and then eventually we'll productize those.
Well, what are you hearing are the big problems? I mean, you're dealing with all the customers that are working at the leading edge here.
Power and thermal are the biggest challenges, and eventually design complexity is going to be a challenge.
And the power is getting the power to the individual transistors?
Yep. And then, getting the power. So backside, TSVs, that's probably the way it's going. The other advantage of the CPO, the co-package optics, is rather than having all the I/O go out through the package, you can come out directly to fibers. So bringing fiber into the package, I think that's going to help with thermal, because it's going to reduce your I/O power, and it's going to help with bandwidth as well.
Yeah, on the power delivery, Ed, everybody knows this, but just to put it in context, taking the 400 volt DC down to 0.8 volts in the chip and in the rack, it depends on how many hops you're going to have. The efficiencies today is in the range of about 70-75%. Barely you get to about 80%. You lose about 20% power there, just the power delivery. Just if you can take it up to 90%, that means you have saved 10%. That's huge. You talk about 50 kilowatts and 100 kilowatt, and if you save 10% of that, and that can be translated to performance if you want to, whichever way you want to use it. But that is a lot of work going on in trying to improve that.
Yeah, there's a lot of work, and as I mentioned earlier, with substrates, but actually putting power planes in the substrate, things like that, even doing cooling in the substrate, glass interposers. Those we have to really come up with new challenges because it's getting worse. And one of the biggest challenges is 3D stacked die for like RF and 6G applications where your top layer is packaged antenna. You can't put a heat sink on top of that. So you're looking into some really exotic stuff. So it's a DARPA hard problem that's just starting, and that's going to be a real challenge. Mixing true heterogeneous, type 3-5 materials and silicon all in a single stack.
To everything, to AMD, everything is a challenge of putting together the chiplets. To Applied Materials, it's a matter of the materials. To Intel, it's the same as AMD. To Latizia and Alphawave, it's a matter of putting all these things together and making them work. Substrate, tools. We have problems that span this entire industry at this point, and even beyond this industry. How do we bring the ecosystem together? Who is going to be responsible for this?
Collaboration is the key thing. We have to work together. Even the EDA vendors, we're starting to work together and trying to standardize that rather than saying, well, take our standard and make that the standard. So that's one step in the right direction.
I think I see a lot of ecosystem now reacting to it. As I said, Vivo was a closed system, so Intel, NVIDIA, AMD doing it, but now we're seeing every aspect of our industry moving and upfronting the chiplet and the advanced package and the 3D integration. So we see definitely JEDEC or OCP, but not only, we see other ecosystem pick it up, ARM, for example, from the architectural point of view. So we see everyone now, automotive with IMEC initiative as well. So everyone now is starting waking up and influence. So there is no one resume, all the area of the ecosystem coming together. So a lot of collaboration.
It's a very, very siloed approach. I think that's what is hurting how fast we can build an ecosystem. I really think, there is product differentiation where we all compete and which we need to, but in terms of standardization and chiplet ecosystem, I think there needs to be some kind of an industry consortium where we don't need to share our IPs, but we should be able to at least go through the complexities of how an ecosystem can be enabled. If we don't do that, it's going to continue to be a very siloed approach.
And this leads back to one very old problem in this industry. How do we share the data that's necessary in order to make all this work?
Yes, so I think it goes to this concept that there are some base standards that really need to be an open ecosystem. So for example, if we are bringing in a chiplet marketplace, design environments in which you can define these chiplets, analysis environments that you can simulate them, we do want those to be open ecosystems that many people can use. I do believe the data sharing, especially with some of the cloud warehouse systems that are out there, can provide an ability for you to share, but not all of it. So for example, if I have a set of validated chiplets, and I feel that that is something that I can contribute to the industry, without necessarily sharing my secret sauce, but you can run a report on it and say, here's what works, or here's a query that basically works on my database. I think that's a win-win for all of us. Because in some ways, no one company will be able to validate every scenario. And so in that sense, even an analysis of a chiplet in a particular architecture is something that may be worthwhile for sharing. But the environment needs to be set up in such a way that whatever a company views as a secret sauce, they still have a way of protecting it. And that's, I think, the work that needs to be done.
Needs to be some firewall.
Yeah, we just did an example with, for example, Intel for interoperability with the UCIe. And so we used their kind of a cloud system, and we did interoperability without seeing any secret sauce from the Intel UCIe file, and they didn't see anything from our file. So there is a way of doing it. I don't think that will stop us. So,
I mean, I have a good example, by the way. If you go look at a 3D Blocks website, Intel is an alpha partner.
Yeah.
You'll see my name and Satish's name there. And we compete, but as we are working together on some of these standards, it's became very critical that we work together on 3D Blocks. We define the chiplet standards and some logical connectivity aspects, and we did play a role in making sure that it goes to the open compute platform, and then we were their partners in taking it and making it an IEEE standard. So again, I think if the intent is good, we don't need to share the secret sauce. We should be able to drive this.
There is another thing that's happening in the industry. It's a little bit further away, but I think you all know processing on encrypted data, which is a very slow thing today. There's not enough compute power that's available, but the homomorphic computing, because this problem that we're talking about, if you take a step back and look at it, it's a universal problem, whether pharmaceutical or as financial or any of those places where there is confidential, sensitive data, but you want to process that. You can expose the content, but you have to process it. So that is coming up. There are quite a few startups looking at it. There's government, funding getting there. But in the next 3 to 5 years, we may have the homomorphic compute.
We will see.
So Ed, I mentioned earlier that, we're building data management into the workflows, and we're using Perforce IPLM. So that is what most of the semiconductor industry is using to manage their data. It can deal with the capacity and the complexity. You can do all the digital threading, and it also has all of the permission capabilities. So we have all that data. The individual users will manage the data in the revision control. This is a meta layer that sits on top of that. And you have the full ability of the administrator to allow who has access to that. And you also have the full traceability. So we're building that right into our workflows.
I think we're out of time, believe it or not. As a matter of fact, we're over time. But I think we've
talking.
only scratched the surface here, so my apologies, but thank our panel. I think they did a great job. And thank you all for hanging in there.